This is 306. In 206, do you guys prove the theorem about diagonalizable matrices? Like if a matrix is symmetric, then it can be diagonalized. Some people do that in 206 and some people don't, like if they go fast enough. So that the assertion is that if a matrix is equal to its transpose, so for example, 1, 2, 3, 2, if you switch the rows and the columns of this, then this row becomes a column and this row becomes a column. And you get the same matrix back again, right? So this matrix is symmetric. So every symmetric matrix can be diagonalized, right? Some matrices cannot be diagonalized. In fact, those matrices, there's a very simple matrix that can't be diagonalized right there. These matrices are so bad, so awful that they get called defective matrices. This is defective. So there's a whole thing you study about eigenvalues and eigenvectors, and then it says, oh, the arithmetic degree of an eigenvalue is not the same as its geometric degree, which really means that the basis for the eigenspace turns out to not be a basis for all the eigenspaces and not a basis for all of R2. There's all this stuff going on in the background with diagonalizable matrices and how much it sucks not to be able to diagonalize them, right? So actually in practice, what happens is anybody, a working mathematician or engineer, if you ever are working with a problem with matrices, you never work with a matrix. You always work with a matrix times its transpose, because this might not be diagonalizable because it's not symmetric. This is always diagonalizable because if I took the transpose of this, you just get the same thing back again. So a lot of engineering scientific applications don't work with these. They work with symmetrized versions of equations because diagonalizing matrices is awesome. Computationally awesome. I don't know. Anyway, so what I'm doing in the measure theory class is we're proving that infinite dimensional matrices are diagonalizable.
So
the annihilator? The annihilator of a differential operator is the annihilator of a function is the differential operator that has that functions that form. That's one version of what the annihilator is. It's not the annihilator in a group theoretic setting, but I don't know, man. You're asking me questions that are so far past the scope of this. 550 is the class, and then I'm teaching two seminars after that I'm not getting any credit for teaching that have 10 people in there. So it's like an extra like 2 to 4 hours of work a week that I do for free because I like talking about math with students. So yeah. Right, what are we talking about? Okay, so the grader, I talked to the grader today. She has picked up your second assignment. She's not quite finished with the first one because she was involved in open house. And she's like the outgoing president of math.
She's a co-same ambassador.
Okay, whatever it is that she is, co-same ambassador. She's been busy with the open house stuff. So I'll get it to you as soon as I can. Are there any questions about anything before we get started today? Like, where is everyone? It's like, oh my God, who made me have a class on Wednesday? I'm going to the bars anyway. Like, all right. So I got asked a question last time, a pointed but good question, which is what is the point? What is the point of all this stuff with the derivatives, right? And it's easy to get lost in trying to build these things up to high levels of generality. So I want to remind you, I'm going to give you an anchor about why we're doing what we're doing here, to remind you what the point of this stuff is. And I'm going to hook it in with the chain rule that we talked about last time, like how the chain rule shows up in practice. So remember that the secret of calculus is that everything is aligned. So remember that really what I want to do generally when I'm working with functions is that I don't want to ever deal with a function. I want to deal with a linear approximation for a function, right? That's the basic idea of computational mathematics is functions are terrible, linear approximations are good. Somebody's trying to get in the room. I will have to admit them. I love Zoom security features. Okay. So what I want to be able to do is in the same way that I do this, a function f of x, a calculus function f of x is about equal to f of a plus f prime of a times x minus a. This basically is the assertion that f has a local approximation near the point x is equal to a, right? Near x is equal to a, f is linear with slope f prime of a. That's like the calculus 1 idea of linear approximation. Okay. So, setting aside a chain rule for a second, I'm going to remind you that the idea with, so for lots of reasons you want to do this. For computational efficiency, you want to do this. For visualizing problems, you want to be able to do this, right? Well-behaved functions are functions that locally look like lines in one variable. In higher levels of variables, we have the same exact relationship. So if you had f taking some domain x contained in an n-dimensional vector space and spitting it out in an m-dimensional vector space, we still have linear approximation. We still have the idea that this horrendously twisting 10-dimensional surface in Rm or whatever, m-dimensional surface in Rm still locally looks like tangent lines. Tangent lines are nice, functions aren't. F at a vector point A is about equal to, I guess here we have vector F, is about equal to, the f of x is about equal to f of A plus df at A times x minus A. The whole point of derivatives and all these extensions of derivatives is to get a way that we can compute these slopes so that we get basically the exact equivalent of tangent lines. The point of derivatives is to give us linear approximations. And basically all of contemporary vector mathematics, physics, engineering, applied mathematics starts from the idea that functions can be replaced by these linear approximations. Okay? And nice functions are those for which we can do this. It's still basically the same exact equation, the point slope equation, but in the vector version. Okay? It's still the basic idea that functions locally look like, I'm going to put quotations around this, tangent lines. Quotations because they're not lines anymore. They're like flat planes in each of the variables, but still locally flat. Good functions are functions that can be approximated with linear functions. So now you say, okay, well, what about the chain rule? What's all this garbage with the chain rule? Why are we making things more complicated? Why can't we just compute derivatives? So here's a situation that comes up frequently when you're working in practice. So somebody might tell you, hey, I've got this function that I'm working with as a model. So here's one, f of x and y is equal to x squared y plus the square root of x squared plus y squared. And they say, can you compute the derivative of that thing for me? You say, yeah, I can do that. I may just compute a gradient, right? The gradient of this function, or the d of f, if you like. Am I really going to do this to myself? Maybe not this time. That's not. You know what? Actually, this is fine. We're only going to do it once. You only live once. Let's do a derivative like this. So df is equal to the x derivative and the f derivative. So your boss is leaning over your neck and said, "What's the derivative?" And you're sitting here like, I don't know, 2xy plus 1 over 2 times the square root of x squared plus y squared, and then there's an x up, a 2x up here. Here's the x derivative. Just take the partial with respect to x. I think that's what comes out, right? X squared plus y squared to the 1/2. The 1/2 comes down. You get a minus 1/2 power, and then you multiply by 2x, which I think is what you get when you do this. In the other slot, you get x squared plus 2y over 2 times the square root of x squared plus y squared. And then when we asked you why you didn't simplify, it's because your teacher didn't make you. 2 over 2 is perfectly valid. Okay, now, so you say, oh, what does a local approximation for this function look like? And you say, well, I know how to do that. That means this function is locally about equal to, if you give me any point A, for any A equal to x naught, y naught, that function f at x and y is about equal to this matrix, sorry, F of X naught Y naught, plus that matrix DF at X naught Y naught times X minus A. Done. You say, I'm all finished. I did it. I found a linear approximation. Then he comes back and says, oh, I didn't want you to do it in rectangular coordinates. I wanted you to do it in polar coordinates. Our entire system rotates. Don't give me a linear approximation in terms of Cartesian coordinates. Do polar coordinates. Oh, that's a bummer, you would say, in this scenario I'm constructing here. So what is actually a polar coordinate? What is polar coordinates? What do they do? I pointed this out at the very end of last time. So how do you change from X and Y into R and theta? If I'm working with polar coordinates, I got equations for X and Y in terms of R and theta. R cosine theta and R sine theta. So recognize that as soon as I write this down, I'm writing an equation, a vector valued equation that takes in an R and a theta and produces an X and a Y. So there's actually an equation here that looks like X of R and theta is equal to R cosine theta, R sine theta. There's an equation that changes R and theta into X and Y values. So if whenever you've changed the function into polar coordinates, what you've really done, usually a grindy, painstaking way, was you actually made these substitutions over here into this equation and then ground out some derivatives or whatever calculations you were trying to do, right? The thing is, you never actually need to do that if you have the chain rule, because you know what the derivative of f composed with x is. You know how to write down a derivative for the original function, but with the polar coordinates substituted in, composed in. The derivative of f changed into polar coordinates, that's what this does. This is the change into polar coordinates. This makes the independent variables r and theta. So if you take f and you change with a change of variables by composing with this function x, and you compute this derivative, you get df in the original variables times dx in r and theta. So to compute a new derivative with a change of variables, which happens all the time in engineering, I don't want x and y, or physics or math. I don't want x and y, I want polar coordinates. All you have to do is multiply by this derivative, which will be the same every single time you change coordinates into polar. Every single time you compose f with a change, whatever f happens to be, this will change because the function changes, but the change of variables that comes from the polar coordinate function will always be the same. The derivative of x equal to, well, it's the r derivative of slot 1. And then the theta derivative of slot 1. And then the r derivative of slot 2. And the theta derivative of slot 2. This right here, this matrix, all you have to do to put the change of variables and get a new change, a new differentiation, a new approximation formula, is just to chain this derivative on the end of your original function. So what the chain rule says is, okay, well, this was this guy. That was my linear approximation near a point A is equal to x naught, y naught. But if you had a point, say, I don't know, z is equal to r naught, theta naught. I don't know why it's z, if it's not something else. It's too variably. About alpha. There we go. Alpha is a good letter. Then the linear approximation is f of r and theta, that is the composition, the composed function, is about equal to f evaluated at x of r naught, f of r and theta naught plus df at the original variable x, which you already know, times dx at r and theta. And now you're going to have x minus alpha. Same equation. The point of the chain rule is I can compose with a change of variables, and the structure of my linear approximation is identical other than the change of variables. The change of variables describes how the derivatives change as you change the variables, but it's a linear relationship, so it just multiplies in. Okay, this is why you learn the chain rule, because the chain rule lets you describe change of variables in a very easy way. This is to your point, why we did the chain rule in linear approximation, right? Is that it kind of fits together. Change of variables are a very common strategy in working with systems. I don't want to consider these inputs and outputs. I'd like different ones instead. How can I fix my model? Well, just put the change of variables in here. Make sense? Ish? Yeah. I mean, your boss has no idea what's going on anyway, probably. It depends on if your boss is an engineer or a business person. At some point up the chain, there's going to be somebody who has no idea what you're talking about, right? Just go do it. All right. Now, so hopefully that gets the idea, even if you didn't follow the exact details here. The idea is simple change of variables are compositions of functions, and they're very easy to keep track of when you're doing linear approximation. And since linear approximation is what we care about the most, the fact that this is very easy to do motivates why we care about this particular approach to studying derivatives. Okay, now we get the best possible derivative. This is 2.6. Gradients and directional derivatives. Okay, remember what a gradient is? When does it even make sense to talk about a gradient? What sort of functions? You could do it for a two variable function, two inputs or outputs. Two inputs. Could you do it three inputs? With n inputs? Could you do it with two outputs? No. Gradients make sense for scalar valued functions. So for the purposes of our conversation today, we're going to assume that f takes a domain in Rn and it maps it into R. And we're going to assume that this function has partial derivatives everywhere. So the gradient is a special derivative that only makes sense for scalar valued functions. Okay, so this is a scalar valued function because it spits out a scalar. Grad f is equal to, what's your favorite notation for partial derivatives? Here's one I haven't used before. dxf, dyf, oh, that's not that. dx1f, there we go. dx2f up to dxnf. I haven't shown you guys this particular notation before, and it just occurred to me that I probably should. Partial with respect to x1 is how you read that. People are always looking for the least, the lowest effort possible notation. This is equal to fx1, fx2, fxn. And if you're really pedantic, remember, you could just write df1, df, dx1, df, dx2, df, dxn. I will warn you that whatever your particular academic discipline is, everyone has a different way of writing this. So you can write down whatever you're comfortable with. Yep. It's a vector. Gradients are vectors, and they have a vector interpretation. So that we want them to be vectors because we're going to interpret them as vectors. Okay. So basically the idea with what a gradient is, and I don't know if you guys remember this or not, the gradient is the vector. And now notice, when you think about this vector here, the number of entries of this vector correspond to the number of inputs, right? So this is not a vector that lives. So another way of thinking about what this function f is actually doing is, maybe we'll just do it in two variables so you can visualize. what these functions are. If I write z is equal to f of x and y, that means f takes some domain in R2 into R. This is called a surface. Remember what I mean by that is there's an xy living down here, but the z is doing is it's going up and telling you what the height of the graph is, right? There's like a sort of a 2D graph sitting over the top of the domain, but this is a surface. Okay. The gradient of this particular function, the gradient of f is going to be equal to fx fy. And notice that does not live in the surface. The surface would take 3 points for it to live, right? 3 points are required to live in three-dimensional space. There's only an x and a y here. So whatever the gradient is, the gradient lives in R2, not R3. So we can think about the gradient as being a vector somehow attached to the domain of the function. The gradient tells you something about what's going on in the domain. Gradient is a vector in the domain. What could that possibly mean? So does anybody remember what the gradient does? A couple of different interpretations of what the gradient means. Yeah. No. It is normal to the level curve, but that, okay, so what is a level curve? We talked about this a million years ago with level curve. A million years ago. A circle. What do we mean? What kind of circle?
Like the different level ones were like K is equal to.
Good, exactly. They don't have to be circles though, right?
Right.
Shapes. Yes, yeah, the curves. Okay, so I'm going to remind you guys that there were these objects called level curves. Level curves are attached to the domain of a function. I'm trying to emphasize this because it's really easy to get confused in the logic of what we're talking about with these. Level curves are in the domain of a function. Say like we're in f of x and y, so we'll say level curves in two variables. And the way we visualize a function in terms of level curves is we go into the domain x, y. So imagine this is the domain of f. And I find all the values that f spits out a constant value. So if I solve the equation f of x and y is equal to c, I'm saying make the z variable always constant. Find every x and y that produces the same output z. Remember we did this thing with the paraboloids where we drew the circles on the graph at the different heights of the thing. So the level curves might look like this. Maybe this is the one where every x and y on this curve spits out c is equal to 1. And every one on this one spits out c is equal to 2. And everyone here spits out c is equal to 3. Those would be examples of level curves. They are the solutions to these equations. Can they touch each other? Is it possible for two level curves to touch? I see this and I see this. So it's a continuous function, but why does that mean they can't touch each other? If they were touched each other and they were associated with different values, that means the function could spit out two different heights for the same input.
That means they're not continuous, right?
It means it's not even a function if it can spit out two values for the same input, right? If I say, here's everywhere the output of the function is 3, and here's everywhere the output of the function is 2, could a function have value 2 and 3 simultaneously? And the answer is no, right? Level curves don't touch for continuous functions. They don't touch for functions at all. They can't. Okay. So level curves don't cross. What's the relationship between the gradient of f? So the gradient of f, so I want to know what the relationship is between the gradient of f and the level curves. Well, I mean, we'll prove this in a minute. I'm trying to remind you guys of stuff you've probably seen before in other contexts. So, and then we're going to interpret what it means with the gradient function. There's a geometric interpretation of what the level curves actually mean, and there's a calculus interpretation. Remember here, this is the domain of the function. These are entries in the domain, right? So somebody said something about normality. What do you mean by that? What does normal mean? Okay. At a point xy, gradient of the function at that point is perpendicular to the tangent line of the level curve. This is one of the most important geometric facts about what gradients do. The level curves of a function tell you where the height is constant. The gradient vectors point perpendicularly to those points. What do they mean? If you were traveling on a tangent line, how would your say this is a graph of a mountain, and you were traveling on a tangent line? How would your altitude be changing if you were traveling tangent to a level curve? Very little, right? So almost none, right? If you travel on one of these level curves, your height never changes, right? So the tangent line represents constant height. The gradient represents the direction of greatest increase or decrease in altitude. The gradient, because it's perpendicular, this you can think about this as constant height. In some previous class somewhere, I guarantee you somebody told you, if you've seen a gradient before, that somebody told you very quickly probably that the gradient represents the change, the direction of greatest change of a function. So gradient of f is, we're going to probe what this means. Direction of greatest change. But we have to be careful about what we mean by that. What it means is, if you move that direction in the domain, the outputs, if you put those values into the function, would change the most. Remember, these are domain values, right? It's not on the surface. These are inputs into the function. The gradient of f is telling you something about the way the inputs act, or how the output reacts in response to changes in the input in that direction. The gradient tells you about changes in input. So the direction of greatest change in the domain. The gradient of a function tells you the direction of greatest change in the domain. We'll come back to this. Maybe we'll prove it. But of course, we have other directions we could have gone. Maybe I don't want to know the direction of greatest change. Maybe I just want to know the how the function changes in some other direction. I mean, that happens. Maybe I want to know what happens if I go this way. If I travel in this direction from x and y, I would also like to know about how much I'm going to change in z if I travel a different direction, right? I mean, there's an infinite number of lines originating in x, y. I could go this direction, which is the direction of greatest change, or I go this way. How much do I change if I go that way? In fact, any direction between here and here, I'm going to have a different amount that I change. And I'd like to know what that is, especially if we throw away our sort of baby example in 2 variables and imagine that there's 22 variables that are dictating the gradient vector of greatest change. And I could vary any one of them. And I still want to know for all these different directions what the change in the surface is with respect to changes in those directions. So that gives rise to the idea of an object called the directional dimension. Gradients are too easy. So basically with a directional derivative, is we define it like this. So directional derivative, we actually do it here. So let definition of the directional derivative. We'll try to explain, we'll try to understand like why the definition works the way that it does. So we'll let x be open. And let's let f scalar valued. And we'll pick a point A inside of X in the domain. If B is a unit vector, as a unit vector, length 1, yeah, direction vector, right? Just a direction. If B is a unit vector, then directional, this is going to be a mouthful, derivative of F in the direction V is, and I'll draw a picture of what's happening. D, B, F, A is the limit as H goes to 0 of F of A plus BH minus F of A all divided by H. What on earth does that mean? I mean, it looks like a derivative. Still a difference quotient. What on earth are we actually measuring here? So let's go back to our picture down here for a second and see if we can figure it out. Imagine that we have some level curves of a function. Here's just one. We pick some point A. That's where the A comes from. Some A that's in the domain of the function, right? I've put on a level curve to emphasize that the gradient lives out here. This is the gradient of F. Pointing in that direction, perpendicular to the level curve. What we're saying is, if you pick any other direction starting at that point, any other direction, so say you pick this direction, we'll call that V. And we say V is a unit vector. What are we doing with this difference quotient? We're saying, in the direction V, go out a little bit. So start at A, go in the direction V, and then multiply that by a number H that's getting smaller and smaller. So I don't know if I'm making this clear or not. What we're saying is, this vector right here is A plus V. That's what gets you to this point right here. This is the vector V. A plus V is this point. This says, go out in this direction here. Then start reducing the size of the vector that you, don't change the direction, right? The V doesn't change, the H changes. Take that vector A plus V and multiply it by an H that gets smaller and smaller and smaller and smaller and smaller and smaller and smaller into the point. What we're doing is we're finding the tangent line to the surface in this direction. So sitting above this is some surface, right? And that surface has a tangent line, and we're computing the slope of the tangent line in just this direction by doing this. It's like we've taken the gradient and rotated it, and now we're looking at a derivative as we come in on this line. This is still a change in Z, but it's a change in Z in this direction in the domain. Okay? So when I say directional derivative, what I mean is, I don't want to go in like the X direction or the Y direction, go in this direction, figure out how the surface is changing, and then look at the tangent line that comes into the point in that direction. So I can choose an arbitrary direction from a point to compute the directional derivative. I'll have a picture of this the next time I come in. I'll show you what directional derivatives actually do, like how you can visualize them. But the idea is, this basically says that you're computing a tangent line to the surface that sits over this specific line instead of this gradient, which you're guaranteed to get. Okay, now, actually, let's actually compute one from the definition, and I'll show you like why you never want. Yep.
The gradient there is normal to what?
The gradient is normal to the tangent line to the level curves. So this is tangent to the level curve. This is perpendicular to that tangent. And it's going to turn out to be the case that we can actually use the gradient to build these directional derivatives, right? That we can actually use this relationship. So we don't ever have to compute this from the definition. We're going to do one example of computing it from the definition, then we're never going to do it again. Okay. But anyway, the idea is that all this does, D, V, F at A. If you don't remember anything else about this, remember that this is the tangent line to F at A in the direction B. Yep.
Is this still the transpose of the gradient?
Transpose of the gradient. No. This, okay. This is an excellent point here. The symbol D gets used in a billion different ways in vector calculus. Okay. The fact that I put this little subscript down here means this is not a matrix. This is not a matrix. Okay. DVFA is not a matrix. It's a vector. I know that's annoying. So we've got, so far we have this pile of symbols. DF with no modifier was a matrix derivative. Thank you for asking for the clarification. That's a matrix derivative. Then we had grad F, which was a vector. And then the directional derivative is going to be the version of the function that exists. I mean, if this is a scalar, right? In this case, this is a scalar. This is just a number, and this is a number, and we've divided it by a number. So this is a number. It's just a slope. This thing is a number. So we've got the same basic symbols being used over and over again for different objects. Yep.
So it's not.
It's yeah. I mean, it's the I should say yeah the slope. Thank you. Yeah, it's the slope of the tangent line on the surface in that direction. So basically, if you were on a sphere, for example, not even imagine that you had. Geez, how do I do this? It's so hard to say without actually having like something I can show you guys how to visualize it. But you can imagine that if you were sitting on a surface, say you're just on the side of a mountain. So you got some mountain that you're sitting on top of, right? And that mountain has some sort of dimension like this. If you're sitting at a point on the mountain, I really like to be able to know how steep my travel is going to be in any direction when I travel up the mountain, right? If I go straight up the mountain versus going sideways along the mountain, along this curve right here, those are really different sort of directions. Here I don't change altitude at all. Here I change altitude in a really steep way, right? But what if I want to climb the mountain sort of in a corkscrew manner where I'm not going straight up and I'm not going sideways? I'd still like to know what my change in altitude is if I choose a different direction than straight up or along the side. And so the tangent line that we're computing is going to give us that slope, because what it's saying is if you rotate it the way you were traveling, there's going to be some tangent line that's still tangent to the mountain, still tangent to the surface, but it's not pointing straight up and it's not pointing straight up the side. It's another arbitrary direction that you chose. So it's like sort of a particular slope that's dependent on the particular direction that you've chosen. So where have you seen this before? Well, I don't know how many of you guys have taken Calc 4. You've seen it, you've probably seen it in Calc 4. If you've seen it, any sort of mechanics, you've seen it as well, because in mechanics, what you do with these sort of, with directional derivatives is you're saying that I want to know like a sense of, if I want to calculate a force in a particular direction or acceleration, I mean, a force is basically acceleration, right? So if you have a force you're trying to compute in a particular direction, you actually might not have the choice of just these two directions. You might want to know the force that's being exerted in an arbitrary direction, right? And that's sort of like what you're computing when you compute directional derivatives, like why you care about this. In particular directions, how much force does an object feel? I'm sorry to constantly be resorting to physical examples, but this is where this math was invented for. Okay, so let's actually just do one real quick. And then I promise that the directional derivative is, we're going to be using the idea. So as much as it probably seems like we're working in the nuts and bolts a lot now, remember that the point of this class is to build machinery up that we can use to do some pretty high level applications. And we're just ending our building of the machinery. Right? And once we've got the machinery built, we can start looking at things like the behavior of curves. We'll look at Kepler's laws probably. derivation, like the derivation with the proof that Kepler's laws hold, all in terms of the sort of things we're building out here. There's a function. Okay, so how about let's pick v is equal to v and w, a unit vector. How about we compute directional derivative in the direction v, pick one, dv at the point 0, 0. So the first thing is to be able to even read the notation. V is a unit vector representing the direction. This says compute the slope of the tangent line to this function at the point 0, 0 in the direction v. Okay. The hardest part about this math is reading what the terminology is telling you to do. Now, the long and painstaking way of computing this is by actually writing down that difference quotient. So that's the limit. Each goes to 0 of f of 0, 0 plus h of vw, h times vw minus f of 0, 0 all over h. Which means I'm plugging in an x and a y, right? What x and y am I plugging in here? So the limit is h goes to 0 of f of hv hw. That makes sense. This is my starting point. This is the vector direction that I went. That's the h that I'm going to be canceling away to calculate the tangent line.
Does it say v comma what?
V comma w. So that's just the definition of the difference quotient that we're after. My anchor point, my direction, and then the direction, the scale that I'm using to collapse into the point I'm interested in finding the slope at. You should never want to do this again by the time we're done. One difference quotient. Yep.
Can you repeat how to read the notation?
Yes, I will. Let me write it down in words. Okay, what this says is, because there's this v floating around down here, I know it's a directional derivative. So I read this as this is, I would read it one way as the slope of the tangent line to f in the direction v at the point 0, 0. So d sub v means automatically directional derivative. The directional, I'm even cheating by calling it a slope, but slope of a tangent line is one way of thinking about it, right? The slope of the tangent line to this function at that point in this direction. All right. Okay, so then what do? You take this HV and HW, you plug it in all over the place up here. What do you get out of this? How did I get that? Ever we saw an X, I put an HV. Ever we saw a Y, I put an HW. I subtracted off f of 0, 0. But what is f of 0, 0? 0, right? That's a pretty simple computation. Notice that this basically should remind you of computing this the one time you had to compute a derivative from a definition back in Calculus 1. It looked exactly like this. You pile in a bunch of numbers, but there, hopefully when you're done, everything cancels and everything left has an H inside of it. And then all the H's cancel out. So after you cancel the H's from the top and the bottom, you get HV squared minus 3HVW plus 2V minus 5W. All the H's that we just distributed the H across this and canceled. Now let the limit go of H go to 0. That's okay now, because now we don't have 0 over 0 anymore. And you get out 2V minus 5W. That is the directional derivative. Yep. By hand? Absolutely not. What I'm trying to do is I'm trying to motivate learning the gradient version of this. Because it's going to turn out to be the case that I never have to do, if I did, okay, let me put it a different way. If I did ask you to do this, I would tell you what the difference quotient was. Right? I'm not going to expect anybody to remember like 18,000 difference quotients. You should remember what the idea of a differential equation or what the directional derivative is, but not, I don't care if you carry around in your head that. Okay. Now there's something weird about this. Something weird about this. What this is saying is, so let's actually interpret what we mean by what I've written up here. So this says that if the vector v that you pick is equal to vw, then dv at 0, 0 is equal to 2v minus 5w. That's pretty weird. That seems pretty easy. But notice that this depends on the direction, right? As you rotate the vector, you change the slope. As the input vectors change direction, the slope of the surface changes. Let's actually see what the gradient of this function is. 2x minus 2y plus 2 and minus 3y minus 5. That's the gradient of the function I wrote down. Right? That's the f derivative and the y derivative. What is the gradient of f at 0? Well, if I put a 0 here and a 0 here, I get 2. And if I put a 0 here, I get minus 5. Oh, that's really weird. I got 2 and minus 5 is the gradient vector. That's the direction of greatest change. But there's a 2 and there's a minus 5 right there. And there's the v and there's the w. So I don't know if I'm crazy, but it kind of looks like the directional derivative in the direction v at the point 0, 0 is equal to the gradient of f at 0, 0 dotted with the vector vw. I mean, that's what that would mean, right? I mean, if this isn't this just a vector 2 minus 5 dotted with the vector vw? Well, that's an odd coincidence. It's almost as if secretly it's going to turn out to be the case that every directional derivative can be derived from a dot product against the gradient, which is one of the strongest features in favor of using the gradient for things, is we never have to do this difference quotient if it was coincidentally the case that every directional derivative of a differentiable function could be gotten by dotting with the gradient. I bet that's something we might be able to prove. If your math professor has gone out of his way to point out that this strange coincidence exists, that this directional derivative in the arbitrary direction vw is also equal to the gradient of the function dotted with the arbitrary direction vw. It's almost like that's where this is going next. All right, so I'm going to close this up. And so what we're going to do with so directional derivatives and the gradient turn out to be an incredibly important idea for analyzing the behavior of functions. And directional derivatives in particular turn out to be really nice to work with because the gradient is going to turn out to tell you everything about every possible behavior of the function. You don't need to know any more than the gradient. Because all that stuff with the difference quotient is going to reduce to a dot product involving the gradient. All right.
I was getting confused because we're doing similar things to 453, but they're all matrices.
Oh yeah, we'll do yeah. It's a little different with matrices. All right, guys. Thanks a lot.